In this video, we're going to talk about the idea of a z-score. A z-score is another statistic that's calculated with a formula, but it's different than the types of statistics that we've been covering in this class. So far in this class, we've been talking about statistics that summarize an entire set of data, like the mean, median, and mode. A z-score doesn't tell you anything about an entire set of data. Instead, a z-score tells you something about a certain data value inside of a larger set of data. A z-score tells you the position of a certain data value inside of the data set. In other words, a z-score tells you whether a certain data value is a typical data value in the middle of the data or a more extreme data value out toward the right end or left end. When a person calculates a z-score, what the person does is the person takes a certain data value and plugs that data value into a formula to turn that data value into a z-score. The z-score then tells the person whether the data value is a typical data value in the middle of the data or a more extreme data value out toward the right end or left end. If the data value turns out to have a z-score of 0, then that data value is right at the mean. It's not extreme at all. If the data value turns out to have a small z-score, then that data value is near the mean. And if the data value turns out to have a large z-score, it means that that data value is an extreme data value that's far away from the mean. Also, if the data value turns out to have a positive z-score, it's above the mean. And if the data value turns out to have a negative z-score, it's below the mean. Let's take a look at a diagram to get a more specific idea of what a z-score is. First step, let's actually look at this definition of a z-score. A z-score is a measure of position that shows the number of standard deviations that the data value falls below or above the mean. Like I said, a data value that's right at the mean has a z-score of 0. Also, a data value that's one standard deviation above the mean has a z-score of +1, and a data value that's one standard deviation below the mean has a z-score of -1. A z-score that's two standard deviations above the mean has a z-score of +2, and a data value that's two standard deviations below the mean has a z-score of -2. I'll give a real-life example to illustrate this idea. Let's imagine that a certain population, like a city, has a mean age of 30 with a standard deviation of 10. That would mean that in that city, a person with an age of 30 has a z-score of 0, because that person is right at the mean. Also, in that population, a person with an age of 40 has a z-score of +1, because that person is one standard deviation of 10 above the mean. Also, a person in that population with an age of 20 has a z-score of -1, because that person is one standard deviation of 10 below the mean of the city. A person in the city with an age of 50 has a z-score of +2, because that person is two standard deviations of 10 above the mean. 30 plus 10 is 40, and 40 plus 10 is 50. Finally, in that city, a person with an age of 10 has a z-score of -2, because that person is two standard deviations of 10 below the mean of 30. 30 minus 10 is 20, and 20 minus 10 is 10. Overall, a z-score goes up by multiples of the standard deviation. If the mean is 30 and the standard deviation is 10, then 30 has a z-score of 0, and you go up by 10 to get to z of 1, and you go up by 10 again to get to z of 2. You go down by 10 to get to the z of -1, and you go down by 10 again to get a z-score of -2. Here's another example. Let's imagine that a certain city, the mean income is 40,000 per year, and the standard deviation of the city is 10,000. That would mean that in that city, a person with an income of 40,000 has a z-score of 0, because that person is right at the mean. If you go up by 10,000, and you go up to 50,000, you get to a person with a z-score of +1. If you go up by 10,000 again, you get to a person with an income of 60,000 who has a z-score of +2. If you start at 40,000, the mean, and you go down by 10,000, you get to a person with an income of 30,000 who has a z-score of -1. If you go down by 10,000 again, you get to a person with an income of 20,000 who has a z-score of -2. In real life, the most common use of a z-score is to measure where a person's IQ stands compared to other people in the general population. We know that the mean IQ of the general population is 100. So a person in the general population with an IQ of 100 has a z-score of 0. We also know that in the general population, IQ scores have a standard deviation of 15. That means that a person with an IQ of 115 has a z-score of +1, and a person with an IQ of 85 has a z-score of -1, because 100 plus 15 is 115, and 100 minus 15 is 85. Also, a person with an IQ of 130 has a z-score of +2, because 100 plus 15 is 115, and 115 plus 15 is 130. A person in the general population with an IQ of 70 has a z-score of -2, because 100 minus 15 is 85, and 85 minus 15 is 70. So this covers the overall idea of a z-score. At this point, I want us to go into the formula that's used to calculate a z-score. A z-score is calculated by taking a certain data value, subtracting it by the mean, and dividing by the standard deviation. This is the z-score formula in symbols. We haven't covered these symbols yet, but we'll cover them in a later video. Let's look at a few examples of using this formula to calculate a z-score. In each of these examples, we're going to take a certain data value and plug it into the z-score formula to turn that data value into a z-score. Here's our first example. A population has a mean age of 35 and a standard deviation of 7.2. In this population, what's the z-score of a person who's 40 years old? To turn 40 into a z-score, we subtract 40 by the mean and divide by the standard deviation. These numbers are all provided in the question. 40 minus 35 is 5, and then 5 divided by 7.2 is 0.7. So in this population, a person who's 40 years old has a z-score of +7. Notice how this z-score came out to a positive number. I told you that when a data value is above the mean, it has a positive z-score. Here's another example. A population has a mean age of 35 and a standard deviation of 7.2. In this population, what's the z-score of a person who's 32 years old? To get the z-score, we take the age of 32, subtract it by the mean, and divide by the standard deviation. 32 minus 35 is -3, and then -3 divided by 7.2 is -0.4. In this population, a 35-year-old has a z-score of -0.4. And it makes sense that this came out to a positive number because 32 is below the mean of 35. Here's one more example. A population has a mean age of 35 and a standard deviation of 7.2. In this population, what's the z-score of a 35-year-old? Well, we already know that this is going to come out to 0 because we know that a person with a data value equal to the mean always has a z-score of 0. But let's use the formula just to show that it's true. 35 minus 35 is 0. When we subtract the age of 35 by the mean of 35, we get 0. And 0 divided by the standard deviation is 0. 0 divided by anything is 0. We just showed that this person, who's right at the mean, has a z-score of 0. Let's now go over a few important points about z-scores. First of all, a data value equal to the mean has a z-score of 0. It's the least extreme value possible. A data value below the mean has a negative z-score. If the z-score comes out to a negative number, you know that the data value is below the mean. A data value above the mean has a positive z-score. Also, a data value further from the mean has a z-score further from 0. The bigger the z-score, the further the data value is from the mean, and the more extreme the value is considered. So, a data value with a z-score of 7.2 is more extreme than a data value with a z-score of 2.4. Also, If two data values are the same distance from the mean, but are on opposite sides of the mean, the two data values have opposite z-scores. That means that let's imagine that a certain data value is 10 below the mean, and another data value is 10 above the mean. Those two data values are the same distance from the mean, but they're on opposite sides of the mean. Those two data values will have the same z-score, but the only thing that will be different is the sign of the z-score. One data value might have a z-score of negative 3.2, and the other data value might have a z-score of plus 3.2. Finally, two data values with the same z-score are considered equally extreme, even if they come from different populations. So, a person in one population with a z-score of 3.2 is just as extreme as a person in another population with a z-score of 3.2. Even if two people come from different populations, they're considered equally extreme if they have the same z-score.